Hello, what I've got here today is a recap of a problem that we were exploring in class. The situation is we have a curve, C, and if you study this in the future, you'll know this as an ellipse. This is the equation for an ellipse in a sort of a rearranged form. Anyway, it says determine the coordinates of the 4 points on the curve that have a normal that would pass through the point 1, 0. So it's a lot to wrap your head around. It's certainly a lot easier if we can visualize it graphically. We begin with the point 1, 0 and the curve C shown here. And then all we have to do is sort of try to visualize lines that would be perpendicular to the curve and go through the point 1, 0. And I found those two. And it took me a little while. I was actually goofing around with points up around here and this, and I missed the obvious that the line's horizontal. It'll be definitely perpendicular to the ellipse because it's symmetrical. And so we get the other two there. And when I look at this, it seems like really logical because if we had the normal pass through the origin, then all 4 of these would definitely pass through the point 0, 0, but so would probably all the others. But when we slide the point off center, it pulls the normals off of the axis, so now they're tilting and falling off the side. That's the way I visualize it anyway. This graph turns out to be immensely informative in terms of understanding the results and how they make sense. So to begin, we need to differentiate both sides of the equation as an operation, and the derivative of a sum is equal to the sum of the derivatives. Then we can't forget the chain rule, which is the number one mistake that people make, keeping in mind here that the derivative of y squared is 2y, and then the chain rule says we must take the derivative of y then with respect to x. So, solving for dy dx, we will subtract 4x from both sides and then divide both sides by 2y, and after I reduce I end up with this ratio, which basically produces slopes of all the tangent lines. So if I know the coordinates of the point, like so they say this one right here appears to be negative 1, 4, I could put negative 1, 4, negative 1 in for the x, 4 for the y, and we would find a slope of 1/2. Notice the tangent line has a slope of 1/2. So that's what this derivative is telling us. But we need to find normals to pass through the point 1, 0. Here's a clever way to get all the normals generated in the same way. Take the opposite reciprocal. So if dy dx is equal to negative 2x over y, then the opposite of dx dy is the reciprocal and opposite reciprocal. Therefore, this formula generates all the slopes of all the normals. So I started riffing, just trying to figure out where to head from this direction now that I have the derivative. One of the things I did was I solved the equation explicitly for y, and that means that my derivative, dx dy opposite, is going to be y over 2x, or here, plus or minus the square root of 18 minus 2x squared over 2x. So 2 different ways to express the slopes of the normals. I wasn't sure if I was going to need this or not, but I don't know, I was just riffing, like I said. We'll see if it comes in handy or not. Now, further exploration reminded me that to find the equation of a line, we use point-slope formula. And in this instance, the point is given to us, 1, 0, and the slope of all the normals is given to us in terms of x and y. That's why we had the derivative. So now we can actually use that slope in the equation of the normal. And now we have an expression that will tell us the relationship between x and y in order for our line to go through this point and have a normal slope to the curve. So in other words, these are the qualifying conditions in order to make these 4 lines. So the equation of those lines must satisfy, after I multiply both sides by 2x, 2xy equals y, I'm going to distribute the y, and then I'm going to collect like terms, or basically subtract xy from both sides, so 2xy minus 1xy is going to be xy. I also added the y to the other side, and I ended up with this expression, or equation rather. And this is the zero product rule exemplar. That is to say, the product of 2 numbers equals 0, then either y equals 0 or x equals negative 1. I'll go back and look at my graph. Here are the 2 places where y equals 0. Here are the 2 places where x equals negative 1. So this turns out to be the key to quick success. I didn't even have to use my explicit form. I got my two solutions. However, I need the coordinates entirely. I can already see 3, 0, and negative 3, 0. I can see those already, and this appears to be negative 1, 4, negative 1, negative 4. But let's bear it out using our tools. The equation is given to us explicitly, or implicitly rather. We substitute 0 in for y, solve for x, we get plus or minus 3. No surprises. But just to verify, it's producing normals whose slopes are going to be 0, and we had the derivative of the normal. We substitute 0 in for y and plus or minus 3 in for x, and we get 0, so both horizontal normal lines. The other true factor is that x equals negative 1. We substitute that in for x, which is going to give us 2 plus y squared equals 18, y squared equals 16, y equals plus or minus 4. No surprise, again, we already saw that coming on the graph. Now we're looking at these lines and examining the slopes of the normals. We can determine the slopes using the point where x is negative 1 and y is plus or minus 4, which gives us the ratio of plus or minus 2. We go up on the graph and see that we can go down 4 over 2, have a slope of negative 2 for this normal, and up 4 over 2 gives us the slope of that normal. So hopefully you gather from this that we have a lot of analytical work to do, but we're going to have a much better sense and a much better sense of confidence with any experiments that we do if we have some technology and some graphical support and make sure that what we're doing here is consistent with what we see over here. So thanks for watching. Have a great day.